Today we're going to talk about acid-base indicators, which are substances that appear different colors depending on what the pH of the solution is. The reason for this is that the indicators themselves are usually very weak acids, and they're at equilibrium with their two different forms, the one where they're together and the one where it's dissociated. And when you add H plus ions, it shifts the equilibrium in one direction or the other. And where it's combined with the H, it happens to be one color, and where it's dissociated in the free ion, it happens to be another color. So you can see here some examples of some indicators. They appear one color as an acid, and then they hit this point where they're transitioning from one color into the other color, and then they're another color at a higher pH. So for this one, it's red, completely red, everything below this pH. So we can't distinguish between a pH of 2 and a pH of 1 with this indicator. But we can tell if something's a 1 or a 13. And kind of in this transition range, we can determine a little bit more precisely what it is as well. Now notice not every indicator is going to change at a pH of 7. Some change much lower, some change higher than that as well. But below a certain point, it's all of one. Above a certain point, it's all of another. And in between, whatever that amount happens to be, you have this equilibrium balance where you've got some of one color and some of another color. So if you look on table M of your reference table, you'll see some common acid-base indicators. And they give you the pH range that it undergoes the color change for. So for example, methyl orange, between 3.1 and 4.4, it changes from red to yellow. So this means everything below a pH of 3.1 will appear completely red. Anything above a pH of 4.4 will appear completely yellow. And anything in between 3.1 and 4.4 is going to be what you get when you mix together some red and some yellow. It's going to be orange. So we've got that represented down here. Now, the pHs aren't exactly perfectly lined up here, but you can see that at very low pHs, methyl orange is red, then it's orange between 3.1 and 4.4, and anything above that, it's yellow. And again, this transitional phase, it would go from a reddish orange to a yellowish orange in here, but I couldn't do the gradient on the computer. Bromethymol blue, between 6.0 and 7.6, changes from yellow to blue. So anything below 6 is completely yellow. Anything above 7.6 is completely blue. And in between 6 and 7.6, you get a mixture of yellow and blue, which is green. Phenolphthalein, anything below 8 is colorless. Anything above 9 is pink. And when you get colorless mixed with pink, you end up with a light pink. That one's a little bit trickier of a color change. Litmus, anything below 4.5 is red. Anything above 8.3 is blue. And anything in between 4.5 and 8.3 would be a purple. Now, when you studied acids and bases in middle school, you probably learned it as litmus is red in acids and blue in bases, which is not exactly true because they kind of leave off this purple transitional range here. But if it's red, we know the pH is below 4.5, so it is definitely an acid if it's red. If it's blue, it's above 8.3, so it is definitely a base. But there is that purple range as well. Bromcresol green, anything below 3.8 is yellow. Anything above 5.4 is blue. And anything in between, when you mix yellow and blue, you get green. Thymol blue, below 8 is yellow. Above 9.6 is blue. And in between is a mixture of yellow and blue, which is green. One thing that I do want to point out is a pH of 7 is usually, at least, not colorless. It does happen to be for phenolphthalein, but for some reason, many people make the assumption that if it's neutral, the indicator is going to be colorless. Well, that is not true. For example, for methyl orange, neutral is 7. 7 is above that 4.4. So a neutral substance would have a yellow color in methyl orange, or the methyl orange would appear yellow in that substance. pH of 7 is in between 6 and 7.6, so it would appear green for the bromethymol blue. So they do have colors even when they're neutral. Now we can determine what color something is going to be based on what the pH is. We can also determine a pH range for a specific substance. For example, if it is red, I know it's, with methyl orange, I know it is below 3.1. If it is orange, I know it's between 3.1 and 4.4. If it's above 4.4, or if it's yellow, I know it's above 4.4. However, if we put together data from a couple different indicators, sometimes we can get a little bit narrower of a range to determine what that pH of the substance is. Again, the indicators aren't going to tell us exactly what the pH is, but it'll give us a range where we can kind of narrow things down a little bit. But putting them together with others, we need ranges that satisfy all of the data that we have. So if we look at an example where we know that methyl orange is orange and bromocressyl green is green, and I want to know what is the pH of this substance. Well, if we take that information, if methyl orange is orange, then I know that the pH of the substance has to be between 3.1 and 4.4. And if bromocressyl green is green, I know that the pH has to be between 3.8 and 5.4. So what I'm going to do is I'm going to create a little number line here, and I want to know for what values of x are both of those equations satisfied. So methyl orange is orange. I know the pH has to be between 3.1 and 4.4. I also know that for bromocressyl green to be green, it has to be between 3.8 and 5.4. I'm going to look for where the data overlaps. Both are satisfied between 3.8 and 4.4. So that means I know that the pH of my solution has to be between 3.8 and 4.4 in order to get the result that methyl orange is orange and bromocressyl green is green. With that, I can also say that I know my solution is an acid. I could also look at these other indicators and say, well, anything between 3.8 and 4.4 is below 8. So I know that phenolphthalein is going to be colorless. I know that litmus is going to be red because everything between 3.8 and 4.4 is below 4.5. So I can also predict what some of my other outcomes are going to be using different indicators. I have 6 test tubes here with 3 of them have acids and 3 of them have bases. So I alternated. We've got an acid, a base, an acid, a base, an acid, and a base. And we're going to look at how the indicators change colors when they're placed in these solutions. The first indicator that we're going to use is methyl orange. So if I put just a couple drops of methyl orange in there, we can see that it starts to turn the solution red. So methyl orange is appearing red in this solution. If we look at table M, the common acid-base indicators, it tells us that methyl orange changes between 3.1 and 4.4 from red to yellow. So because this is red, we know that the pH of this solution is less than 3.1. When I put a drop into the second test tube, we can see that it's appearing a yellow color. So we know that it changes from red to yellow between 3.1 and 4.4. Since this is yellow, we know that it must be a pH above 4.4. Now that doesn't tell us whether it's an acid or a base, because anything below 7 is an acid. All we know about this solution is that its pH is greater than 4.4. Next, we're going to take a look at bromethymol blue, which changes from yellow to blue between 6.0 and 7.6. So a drop in here. Which we might need another drop to get it to see pretty well, but that is a yellow color, which tells us that the pH has to be below 6 because it's lower than that first color that's listed on, or it's still the first color that's listed, so it must be below that first number listed on table M. And then the next one, when I put the bromethymol blue in there, is blue. So since it's appearing the second color listed, we know that it must be above that second number. So the pH of that solution, because it's appearing blue, we know must be greater than 7.6. And the last one we're going to do is phenolphthalein. Phenolphthalein changes from colorless to pink in a pH range from 8 to 9. So if it's below 8, it's going to be colorless. If it's above 9, it's going to be pink. In between, it would be a mixture of colorless and pink, which is a light pink. So here I'm going to put some into the first solution, and there's no color change. It's still colorless. So we know that the pH of this is below 8. And in the second one, it's turning a nice bright pink color, so we know the pH is above 9. So using the color changes that we see, we can determine a range of pHs for a particular solution. Now, if all I have is this, the acid that I put the methyl orange in, I know that it's less than 3.1. But sometimes if I put that data together with some of the other data, like this one, it was the same acid. This one tells me it's less than 3.1. This one told me it's less than 6.0. This one tells me it's less than 8. Putting all of that information together, I know that the pH must be less than 3.1. If all I had tested was the phenolphthalein, all I would be able to say is it's less than 8. But by combining the information from different tests, I can sometimes narrow down that range. So I just moved it so all the acids are on the left, all the bases are on the right. So I had the acid with the methyl orange, with the bromethymol blue, and with the phenolphthalein. And then the base with the methyl orange, the bromethymol blue, and the phenolphthalein. So again, from the tests, I know that it's less than 3.1, less than 6, less than 8. The only pH range that satisfies all those things is the pH being less than 3.1. All right, now if I look at the bases, this one told me that the pH was greater than 4.4. When I have the blue, I know that it's greater than 7.6. And with the phenolphthalein, I know that it is greater than 9. So putting all that together, I know that anything that is greater than 9 is also greater than 4.4 and is also greater than 7.6. So I now know that this base has a pH that is greater than 9.0. I still can't tell exactly what that pH is, but I have a better idea of what range it's going to be.